All right, today we are going to talk about Gibbs free energy. As stated yesterday, there are two factors that drive a chemical reaction into being spontaneous, or the word you should be using is thermodynamically favorable. What that means is when we mix the reactions together or place the substances into a reaction vessel, that the reaction will proceed to completion. These are always going to be non-equilibrium reactions because equilibrium reactions never go to completion because of the ability to go back and forth. These are going to be non-equilibrium reactions. And therefore, if they are thermodynamically favorable, they will form products at these current conditions. Again, the two things to consider are going to be the entropy of the system, delta S, which is going to be looking at, is there more disorder in the products? Is there less order? Are the products that are formed more chaotic? Look at the states of matter. And again, from yesterday, the solid state is has the least entropy. Liquids come next with more entropy. Aqueous ions have more, and then gases have the most. So if we're going to a state that's further right, we're going to see an increase in entropy. The other factor to consider is enthalpy, back from Unit 2. That's the heat of the reaction. And again, for a reaction to be thermodynamically favorable, we are looking at a delta H value that is going to be negative, or an exothermic reaction, because that extra energy can be used to liberate and give to the reactants to make that heat cause molecules move faster, and therefore to be able to break the energy of activation, the activation energy, and have a successful collision to form products. We see here, first of all, is the second law of thermodynamics. Yesterday we saw the third law, which stated that a purely crystalline solid at 0 Kelvin has 0 entropy. All things have entropy unless it is in that situation. And of course, absolute zero being a theoretical impossible, all things will have an entropy value associated with them. The second law of thermodynamics pretty much states that the universe is tending towards chaos. The entropy of the universe is steadily increasing, and entropy of the universe favors a chaotic nature. Free energy, or Gibbs free energy, developed by Dr. Gibbs in the late 1800s, was a way that we could utilize both entropy and enthalpy together and see which factor was the more dominant factor in determining if a reaction was going to be thermodynamically favorable or not. Through his calculation and formula, which we see right down here, the Gibbs free energy equation allows us to take into consideration the enthalpy of reaction, the entropy of reaction, and then also capital T is the temperature of the reaction. The temperature of the reaction must be in Kelvin. So his equation, if delta G has got a value that is negative, or as you can see here, less than 0, the reaction is thermodynamically favorable. The reactants will form products under the current conditions. If delta G is positive or greater than 0, the reaction will not form products. And if delta G is at 0, then we are at a state of equilibrium. Neither side is favorable because both reaction rates are equal to one another. One big thing, as I said a couple days ago in this unit, is to be able to look at the reaction and be able to predict if it's going to be thermodynamically favorable just by looking and knowing some different conditions. One big thing is something called sign conventions. If you know the signs of each of the substances, you can use the Gibbs free energy equation to predict the sign or if the reaction will be thermodynamically favorable. For example, here in the first one, if delta H, or the enthalpy of reaction, is greater than 0 or it has a positive value, and delta S has a negative value or less than 0, the reaction is endothermic, which we know is not thermodynamically favorable, and a negative S means there's a decrease in entropy, and therefore it is also not favorable. So both conditions are not favorable. If both conditions are not favorable, we are going to get a delta G value that is going to be greater than 0. We can see that by plugging in over here into the equation. If delta H is positive and delta S is negative, the absolute temperature can never be under 0 or a negative number. Therefore, we're going to have a positive number minusing a negative number, which when we minus a negative, it makes it positive. This result is going to always give a delta G value that is going to have a positive value overall. So this is called sign convention, something you get very comfortable with going into the national exam. Plug in if you need to, plug in an arbitrary number and plug in 298 degree Kelvin and plug in a positive H and positive S and see what happens to the delta G value if you have to plug in numbers. Otherwise, some of you can just see it by looking at sign conventions. If the enthalpy of a reaction is negative, exothermic, and entropy is positive, or there's an increase in entropy, both conditions are thermodynamically favorable, and that will always cause the G value to be less than 0 or negative. So in the top reaction, no, the reaction is not spontaneous or thermodynamically favorable. The second one it is. And it is always. It will always never be, and will always will be for those two reactions when those are the signs. What happens when we have competing factors? If we have an endothermic reaction, but an increase in entropy, so entropy is thermodynamically favorable, but the enthalpy is not. In order for delta G, if delta H is positive and delta S is positive, we're going to subtract one number from another number. The only way that G could be negative is if the T delta S term is greater than the delta H term. The only way that this can happen is if we look at the temperature. This reaction can be negative or less than 0 if the reaction is at high temperatures. Lastly, if we have an exothermic reaction, a negative delta H, it is enthalpy driven. Entropy is also negative, which means there's a decrease in entropy. So here the enthalpy term is favorable, but the entropy term is not. The only way, again, this value can be negative or less than 0 if we are now not at high temperatures but low temperatures. At low temperatures, now the delta H term is greater than the product of the T delta S term. And if the enthalpy term is larger, then it's going to cause G to be negative through sign conventions, which should make sense. If you have an endothermic reaction, okay, energy is needed, so at higher and higher temperatures, we have enough energy to supply to the reactants that products can form. We just got done talking about exothermic reactions for equilibrium. Exothermic reactions, if we're at low temperatures, then typically the reaction can be driven forward because that energy will be pulled away from the reaction and more products can be formed. So delta H, or the enthalpy term, is always the primary factor whenever we are at low temperatures, and the entropy term is always the primary factor at high temperatures. I will put on Canvas a little sign convention note sheet that's useful to look at, but get prepared. You'll have the homework now, the first page homework that I've placed on Canvas. Please try to do those problems now, where now you're utilizing and trying to figure out the sign conventions of both delta H, delta S. And once you know the signs of delta H and delta S, then you can use the Gibbs free energy equation to see if the delta G term will be either positive or negative. All right, now we're going to go ahead and look at how we can calculate or plug and chug into the Gibbs free energy equation. Very simple equation, as you can see before. Now again, whenever we have those little not symbols, as we've talked about all year long, that not symbol again means standard states. And that's thermodynamic standard states, again, which is 1 atmosphere and 25 degrees Celsius. Not 0 degrees Celsius. That's STP for gases and gas laws. All right, so this reaction we have is one we saw in the previous lecture, where we have iron 3 oxide, which is reduced by hydrogen gas to produce iron and water. And again, if it's a thermodynamic reaction, states of matter is very important. The water wasn't gaseous, the iron is solid, hydrogen is obviously gaseous, and the iron oxide is solid. And there should be a 3 in front of the hydrogen, and a 3 in front of the water, and I believe a 2 in front of the iron. So this is a reaction that we did yesterday, and we were able to calculate, or I did yesterday, we were able to calculate the entropy of the reaction by going ahead and taking the products, the iron and the water, minusing the reactants, making sure to multiply each of the values of the entropy values of these substances by the coefficients if there are any. And yesterday we determined this reaction to have a value of 0.1415 kilojoules per mole Kelvin. I looked up the enthalpy values just before this audio lecture, and I calculated the enthalpy of the reaction to be 98.8 kilojoules per mole. So if we look at this, we can see that currently at 25 degrees Celsius, we have an endothermic reaction, which is not thermodynamically favorable, but we do see an increase in entropy, which is thermodynamically favorable. And if we look at the previous page, the lecture notes we just talked about, this reaction will occur as we get higher and higher temperatures. All right, so let's see at standard state conditions if that's the case. So to calculate delta G now, we just go ahead and do a plug and chug. So we plug in the enthalpy value of 98.8. It's critical here that the units match, so we have kilojoules per mole, minus the temperature has to be in Kelvin, so 25 degrees Celsius is 298 Kelvin, times 0.1415 kilojoules per mole Kelvin. You can see now why entropy has units of Kelvin in it as well. The Kelvin units will cancel through this multiplication, and we're going to be left with a number that's in kilojoules per mole, which matches the enthalpy value units of kilojoules per mole, and therefore we can add, in this case, subtract the values. When we subtract, we get a Gibbs free energy value at standard conditions, at standard state conditions, to be 56.6 kilojoules per mole. Since delta G naught is greater than 0, it has a positive value. This reaction currently is not thermodynamically favorable. So, if on the national exam they ask you to provide justification as to if a reaction is thermodynamically favorable, you're going to want to calculate a delta G value. If the delta G value is positive, that is your mathematical support and proof of why it is either thermodynamically favorable or not. So in this case, you would say no. So, as I said just before, because this is an endothermic reaction, if I continue to increase the temperature, eventually the T delta S term will get larger and larger and larger. Eventually it's going to eclipse the enthalpy value, and therefore the reaction will become spontaneous or thermodynamically favorable. Let's see at 500 degrees if that changes. Now, at 500 degrees, we are no longer looking at standard state Gibbs free energy equation. Now we're looking at the non-standard state thermodynamic equation. So now I know what some of you are thinking. Do I have to now go back and recalculate a delta H value at non-standard and delta S at non-standard? Actually, no, it's not that difficult at all. What scientists have found out is that the Gibbs free energy value, we still can use the enthalpy value at standard states and the entropy value at standard states. It's the temperature change that is going to cause the most significant change in the value, which will then allow me to calculate delta G. So whenever you're calculating a delta G, you can use the standard state H and S values even if you are not at standard states when you're calculating a delta G value. So that's very easy to do. You just got to change the temperature value. So we're going to use the same exact numbers that we just did before. I'm not going to put in the units this time. 500 degrees Celsius, we still got to make sure it's in Kelvin. So that'll be 773 Kelvin times, again, 0.1415. And when I did the math, it came out to being negative 10.6 kilojoules per mole. So now we see delta G is a negative value or less than 0. And now, yes, this reaction is thermodynamically favorable. Okay? So temperature critical concept that eventually causes that term to become large enough or small enough for it to be able to overtake the enthalpy term. Now, because of this, as we see, because we got a positive and a negative value, obviously there must be a temperature at which the reaction is going to convert from being not spontaneous to spontaneous. And that is when we get the delta G value to be 0. If they ask at what temperature does the reaction become thermodynamically favorable, we're going to take that Gibbs free energy equation and we are going to set delta G equal to 0. Since we know the enthalpy and entropy of that reaction, if I rearrange this equation, if I move the delta H value over, it becomes negative. The two negatives cancel. And what we get here is the temperature can be easily determined by just simply taking the enthalpy term and dividing it by the entropy term. So if we do that, the enthalpy for this reaction was 98.8 kilojoules per mole, and we're dividing that by 0.1415 kilojoules per mole Kelvin. The kilojoules per mole will cancel, and the kelvins will come up to the top, and this temperature is at 698 Kelvin, or 425 degrees Celsius. Now, this is the temperature at which the reaction reaches equilibrium. So if you really wanted to be exact with this problem, you would have to state that the temperature would need to be greater than 425 degrees Celsius. And when it does get over 425 degrees Celsius, delta G now will end up giving us a negative value, and that will that will tell us that the reaction now has become thermodynamically favorable. The reaction will proceed to form products. Hope this all makes sense. Now go to your homework problems and go ahead and give them a try. I have uploaded the answer keys, and the first page is looking at sign conventions, which was the previous page, and the second page now is looking at the second set of reactions. So then you can start plugging and chugging and using those thermodynamically set table values to work with. Thanks a lot for listening.